Okay, sorry, took me a second to get everything set up, but so I have a general request to go over just calculating absolute max and mins. Is there anything else that you guys know off the top of your head that you would like to go over? Okay, so let's just start with, and just as a heads up, I put 11.5 on there, but I'm more than happy to go over 11.2b as well, since we haven't gotten a chance to cover that in discussion. But let's go over problem 41. This was your notebook problem from 11.5. And you are given f of x equals x squared plus 4, all under negative x squared. And we are asked to find the absolute extremum, if any, given by the second derivative test for each function. Okay, so maybe before I do this, actually, let's go over the second derivative test. Okay, so we have some value c that is a critical point, and if we have that the second derivative is positive, second derivative is negative, and equals 0. Those are the three cases we could have dealing with the second derivative. And each one of those cases kind of tells us a little bit about what's going on with the function itself. So this second derivative test is kind of nice because it's just a much quicker way to find minimums and maximums without having to do a sign chart or anything. So when we know that when the second derivative test is positive, that means that we are concave up. And we can already see, based off of the concavity, that we're going to have a minimum there. And then the opposite is true when we have concave up. That's going to be a maximum. But this case, we can already see that we can't gather anything about concavity. All we know about when the second derivative is equal to 0 at a value, that could be an inflection point. It could be a possible inflection point, but we don't know anything about concave up or down. So what we say there is it's inconclusive. We don't know what's going on there. That's kind of the rough guidelines for our second derivative test. And I'm going to put over here, C is a critical point. And I saw that there was something in the chat, so 89, awesome. Yep, I'll go over that next. Okay. The other part that we got from 11.5 is a theorem, theorem 3. Doesn't really matter the number by any means, but it says that if we have only one critical point in an open interval, so that's like a parenthesis kind of thing, if we have only one critical point in an interval, then that is going to be an absolute extrema there. Okay, so that's just something to kind of keep in mind there. So we can only have absolute extrema on an open interval if we only have one critical point. Okay, now that we have all of that background information, let's get into 41 now. So for 41, like I said before, they're asking for absolute extrema, if any, using the second derivative test. So we can see that to use the second derivative test, we need a critical point. How do we find our critical points? A little bit of review here. So remember, we get our critical points from our first derivative, where our first derivative is undefined or equal to 0. So step 1, find critical. And I'm going to put points in parentheses because we may have more than one, we may not. So we need to find our first derivative. What do we need to use here to find this derivative? Chain rule, product rule, quotient rule, power rule. What are we using?
Quotient rule.
Quotient rule, exactly. So quotient rule tells us we always start with the bottom. So we have bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, and then just rewriting this, derivative of negative x squared, that's just going to be negative 2x. And then I'm going to actually just rewrite this as a plus x squared times derivative of x squared plus 4, that's just going to be 2x all over x squared plus 4 squared. Okay, now we're just going to condense things a little bit. We'll have a negative 2x cubed minus 8x plus 2x cubed. X squared plus 4 squared. We can already see up in this numerator that these two will cancel out. So that leaves us a pretty nice derivative to work with. Okay, so we have our first derivative. That's step 1A, we'll say, of finding critical points. Now, what do we do with this first derivative to find our critical points? Well, critical points occur where the first derivative is either equal to 0 or not defined. So let's start with not equal to 0 first. And remember that whenever we have a function that has a numerator and denominator, when we're looking for where the derivative is equal to 0, it's equivalent to saying just where the numerator is equal to 0. It's a really nice feature there. So that just gives us x equals 0 as a critical point, which is really, really nice. How can we find where the function is undefined?
Would it be the bottom equal to 0?
Exactly. When you're looking for where the derivative is undefined, you want to look for where this denominator is equal to 0. So we'll just say that as is. And whenever we just are setting something equal to 0, we can just get rid of the squared. I have x squared plus 4 equals 0. Okay, can we ever have a squared term equal to a negative term? Can that ever happen?
It can, but it's an imaginary number.
Yes,
Right?
yes, that's a good way to clarify. So the only way you can ever have a squared term be negative is if you're dealing with imaginary numbers. But in this course, we're only focused on real numbers. Imaginary numbers are not a thing in this course. So we're going to say that can't happen. So what that means is we have only one critical point. So if we have only one critical point in an open interval, because we're looking at negative infinity to infinity, what does that mean? Are we going to have absolute or local extrema?
Wouldn't it be absolute?
Exactly. When we have only one critical point in an open interval, that means we have absolute. Okay, so now we have our critical point. Our last part is just to find second derivative and then plug this number in. So let's find our second derivative. Okay. F double prime of x. What are we going to have to use again to find this the derivative of this function? Which rule? No one? Okay. So we're going to use quotient rule again. So we're going to start with the bottom. So I'm going to have to zoom out a little bit here. So we're going to have x squared plus 4 squared times the derivative of the top minus the top times the derivative of the bottom. Okay, and then all over the bottom squared. Okay. It's a little ugly, but it hopefully will come together kind of nice. So this term will stay the same, x squared plus 4 squared. That derivative will just be a negative 8. Going to turn that guy into plus 8x. How do we find the derivative of this term? What do we
Chain.
chain rule, exactly. So we're going to have outside, which is the squared. So we're going to bring the 2 down, leave the inside alone. Sorry, that's my dog. And then times the derivative of the inside. Okay. And then what happens here when we square a squared term?
It becomes a fourth power.
Exactly, exactly. Okay. Now that we have all our derivatives taken care of, we just need to do a little bit of simplification. So whenever you have a squared term, you can't distribute like you would normally. Anytime there's a power here, you can't distribute. So I'm just going to write simply negative 8x squared plus 4 squared. I'm not going to do anything with that term. And then here, we're going to have plus 8x times 2 times 2x. So 8 times 2, that's 16, and then times another 2, that's 32. So we're going to have 32x squared times x squared plus 4. All over x squared plus 4 to the 4th. Awesome. Okay. Is there anything we can factor out of that numerator? Anything that's common in all of that?
X squared plus 4.
X squared plus 4, awesome. So we can just factor out an x squared plus 4. And then we're left with, we'll have 1 x squared plus 4 left here. So we're going to have negative 8 times x squared plus 4. And then plus just 32x squared. And then still divided by x squared plus 4 to the 4th. Now we can cancel these guys out. And we can combine terms here. So we're going to have negative 8x squared minus 32 plus 32x squared all over x squared plus 4 cubed. Okay. So 32 minus 8. What is that? Anyone know?
$26.
Not quite. Really close. Really close.
24.
24. Yep. Okay, and that's all I'm really gonna do. You can factor out another 8 from the numerator, but you won't really cancel much. So we're just gonna leave it as is. Because really our only goal with the second derivative is just to plug in our critical points. So actually some of this stuff wasn't all that necessary because all we needed to do was just plug in numbers. So now we're gonna say plug in critical point. F double prime of 0, because remember our critical point was x equals 0. 24, 0 squared minus 32 all over 0 squared plus 4 cubed. Okay, so in the numerator we're going to have negative 32. What about this denominator? We're going to have what cubed?
We're going to have 4 cubed.
4 cubed. And that's all the math I'm going to do. Because right now, is this going to be positive or negative? What can we see?
It's going to be a negative.
It's going to be a negative, exactly. So if the second derivative is negative at our critical point, let's look back at our second derivative test. What does that tell us? Do we have an absolute max or an absolute min?
We're going to have a max.
Exactly. So we say absolute max at x equals 0 of, because we want to say what the maximum is, of our function evaluated at our critical point, and then whatever that number would be. Okay? So any questions over using second derivative tests to find max and min? Okay. So if there are no questions, then let's look at a problem from 11.2b. Oops, that's weird. B. Okay. And it was problem 89. Let's look at this guy. So we are given the price demand equation of P equals 10e negative x for x between 0 and 5. And we are asked to find the local extrema for the revenue function. Now this is going to be a bit of a review. We have a price demand equation. How can we get our revenue function? What's our revenue function?
Was it x times p?
Exactly. Revenue is price times demand. But in this case, we already have the price demand solved in terms of one of our variables. And we can do it, but it's not quite straightforward to go back the other way. So we want our revenue to be in terms of x. So what that means is we're going to have x times our price equation, which is x times 10e to the negative x. Okay. We want to find local extrema for this function. Okay. So same as we did before, to find local extrema, we need critical points, right? So to find critical points, we need our derivative. What are we going to use to find the derivative of this function? You can kind of already see over here based on how we created it. Which rule are we going to use?
Was it the power rule?
The other one with a P.
Product?
Product rule, exactly, exactly. So our first term is 10x, and our second term is e to the negative x. So we're going to have first times derivative of the second plus the second times the derivative of the first. Okay. What's the derivative of e to the negative x? You guys know?
Wouldn't it just be e to the negative x?
Really close. What are we missing?
Wouldn't it be times -1? So it'd be negative e?
Exactly. Yep. It'd be a negative e to the negative x. And then over here, we're still going to have e to the negative x, but then it's just going to be multiplied by 10. So we should already be able to see that we can factor a couple things out of this equation. What can we factor out? What do you think? Well, we know we can factor out a 10, right? Because we have a 10 here, we have a 10 here. So we can definitely factor out a 10. Is there anything else we can factor out?
E to the negative x?
E to the negative x, exactly. So then we're left with a negative x plus 1. And it's always really, really nice to have this factored form whenever you're dealing with finding local extrema. Because now when we go to say, set this equal to 0, we have a much easier form to work with. And the other thing to note here that I'm going to put, this function is never undefined. Or another way to say it is it's always defined. Okay? So we just have to worry about where it's equal to 0. Now, e to the x is e to the negative x here. Is e to the negative x ever equal to 0?
No.
No, it's not. So what we can actually do here is we can just kind of ignore it and just focus on this piece right here. Just don't have to worry about that one because e to the negative x is never 0. Okay? And we can pretty quickly see that we're going to have x equals 1 for our critical point. Okay? Now, the thing that's really, really nice here is we have a closed interval. So when we are looking at local, well, actually, I guess that they're just asking for local extrema. Never mind. Okay, so we have our critical points. Now what do we want to do? Think back to 11.2 before you knew about second derivative test. What did you make?
Make a sign chart.
Exactly, make a sign chart. So we're gonna have 1, and then we need our interval here. This is x, this is, oops, not f, r prime of x, and we're 0 here.
Quick question.
Yes,
Where'd you get the 5 from?
from right up here.
Oh, okay. All right.
Yep, it was just given in the problem. Okay, so now let's look at our factored form right here. Okay, e to the negative x, I'm just gonna sketch that out for you guys really quick. That looks something like this. Okay, doesn't really matter exactly what it looks like, but the main point is it never crosses the x-axis. So what that means is e to the negative x is always positive. So same as how we just ignored it when we're solving for x, we can kind of just ignore it when we're worrying about the sign too, because it's always going to be positive. It doesn't change. So looking at negative x plus 1, when we have a number that is less than 1 for x, is this going to be positive or negative right here? Looking at a number less than 1, say like 1/2. It should be positive, because when we're talking, maybe it's easier to see here. If we plug in 1/2 right here for x, we're going to have 1 minus 1/2. That's going to be a positive number. Okay, now let's look between 1 and 5. Say we choose 2. Is this going to be positive or negative here?
Negative.
Negative, exactly. So that tells us that we are switching from increasing to decreasing. Thus, what do we have going on at x equals 1? Do we have a min or a max?
We have a max, right?
Yep, exactly. So we have a local maximum at at x equals 1 of r of 1. That's just plugging in 1 into the revenue function. Okay. Any questions on this first part? And this was part, we'll put A here. Okay. Any questions? Oops. Okay. So, and then if there are no questions, then let's move to part B. So part B is asking for the intervals where the graph is concave up and concave down. So we kind of talked about it with the second derivative test, but where do we get concavity from? Where can we tell if a function is concave up or down? What tells us that?
Our second derivative.
Yes, exactly. Our second derivative tells us whether the function is concave up or down in an interval. Okay, so we already did half the work. We already have the first derivative. So let me just rewrite that down so that we have it. So it was, I'm gonna actually write the factored form. It doesn't really matter, but it just might make it a little bit easier. So now we want to find our second derivative to get intervals where it's concave up and concave down. So same as before, we can use the quotient, not quotient rule, product rule. Okay, so we're going to have first times the derivative of the second plus the second times the derivative of the first. Okay. So this term's going to stay the same. It's still going to be 10e to the negative x. And then this one is just going to be a negative 1 plus 1 minus x. What did we already say is the derivative of e to the negative x?
It's negative e to the negative x.
Negative e to the negative x. So then we're just going to multiply that by 10, and we'll have negative 10 e to the negative x. Okay. So same as before, what can we factor out of here? Is there anything in common?
Is it 10e to the negative x?
Exactly. We can factor out 10e to the negative x again. We're left with negative 1 minus, because we're going to keep that minus sign, 1 minus x. Okay, and then just simplifying that a little bit, we're going to have, so this is going to turn that into a plus, so we're going to have x minus 2. Okay. Now that we have our second derivative, we're actually just going to repeat everything we did up here, but just for the second derivative. So again, we want to look and say that this is never undefined. We always kind of want to make a note of that, whether or not the derivative is undefined, and it's not. So then we can just go ahead and look at where it's equal to 0. And same as before, this e to the negative x is never equal to 0, so we're just going to kind of ignore it and just focus on where x minus 2 equals 0. And that will give us x equals 2. Now the difference here is this is a possible inflection point. We won't know if it's an inflection point until we make our sign chart, because remember, it can only be an inflection point if it changes sign across it. With critical points, it's a critical point regardless of if the derivative changes sign. This is always a critical point. Here, it's a possible inflection point. Just wanted to make that difference. Okay, and then again, same as before, we're gonna make our sign chart. This time for our second derivative. Okay. So again, this 10e to the negative x, that's always positive. So we can just look at what happens with x minus 2. So when we take a number between 0 and 2, say 1, and plug it into x minus 2, is that going to be positive or negative?
Wait.
Yeah.
Yeah, it's going to be a negative.
Negative, yep. Awesome. And then if we take a number between 2 and 5, say 3, and plug that into x minus 2, are we going to be positive or negative?
Positive.
Positive. Awesome. So that tells us, remember, when you're positive, you are smiling, and then when you're negative, you're frowning. Okay? So where are we concave up, and where are we concave down?
We're concave up from 2 to 5 and concave down from 0 to 2.
Awesome. Okay, now what goes on the outside of this one? Brackets, parentheses, a mix?
I think it's just parentheses, right?
So it's parentheses around the inflection point, but since we have working with a closed interval, we're going to end them with a bracket. And the only reason why we're doing that is because we were given that we are working with a closed interval. So this is the same thing as saying x in 0 to 5. Okay, closed interval. So we're just going to denote that here. So that's really all that this problem was asking for. Are there any questions?
This isn't about really this question in particular, but on my math lab, there was a problem where it asked you to determine which graphs were which based on like graphs. It was just like f prime, f double prime, and then f of x.
Mm-hmm.
And it didn't give you any numbers or anything. Right? And how are you supposed to figure that out? That was a little tricky.
So that would kind of be like problems 13 through 16. So let me just kind of generally write that out for you. And so it's like this, from A to B. And is this kind of what you saw?
Yeah, that was it. And it gave us like 4 choices and we had to pick one of them.
Mm-hmm. Yep, so I'm going to show you how you can work through those ones. Because you really don't need numbers necessarily. And like that. Okay, so my drawings are not perfect, but you kind of get the idea. I'm going to move these closer. That's bothering me. Okay, so for this graph, are we increasing or decreasing?
We're increasing.
Increasing. So what does that mean in terms of the first derivative? Is that going to be positive or negative?
Positive.
Positive, exactly. And are we concave up or concave down?
We're concave down. Okay, I see. Yeah.
Yep, awesome. I think you already got it figured out. But then what does that mean for the second derivative?
It's negative, right?
Negative. Exactly. So given this information or given the graph, you can work in either direction. Just kind of following that checklist. Are we increasing, decreasing, concave up, concave down? And you can find that information for each of these graphs without even knowing what these numbers are. Does that make more sense?
Yeah, yeah, but I just figured it out right when you explained it to me.
Yeah. Awesome. Are there any other questions?
Yeah, you made a little chart about like f of the critical point up at the top when it's equal to like the max. Can you just go back to that so I can get it in my notes?
Absolutely.
All right, thank you.
I will post these as well. Yeah, are there any other questions for me? We still have about 10 minutes left of formal discussion. So I'm more than happy to go over anything. I will tell you guys though that your quiz today is over 11.2b and 11.5a. So it's not just 11.5a, just as a heads up. Any more questions for me?
No, I think I'm good. Thank you.
Absolutely.
I'm good as well.
Okay, so if there are no more questions, then I think we are all free to go. I will have these notes posted, and then I will also post the recording of the session today. But have a good rest of your day, guys.